Hello, and welcome to Palisade Corporation's webcast, How Capable Are Your Capability Metrics? Using at-risk to demonstrate their limitations. Presented by Rick Haynes of Smarter Solutions Incorporated. My name is Jamison Romeo Hall, and I will be your host today. And I'll be available to help answer WebEx technical questions by chat. If you experience technical difficulties joining this WebEx session, please dial 1-866-229-3239. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the chat icon located in the floating toolbar. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead products, At-Risk, and the Decision Tools Suite. We invite you to sit back and relax and enjoy today's presentation. Rick, you have the presenter ball.
Hello, this is Rick Haynes. I'm not sure where you are. I am sitting in Austin, Texas right now. I'm going to talk about Cpks and using simulation software. I'm in the process of not sure what hit your screen, but I will be. Let's see, Jamison, can you see my first slide now?
Yes, it looks very good.
All right, sorry about getting there. Again, Rick Haynes. I'm a statistician, and I'm also a Lean Six Sigma Master Black Belt is my other title. I've been an at-risk user for 10, 12 years, both as a statistician and within the Lean Six Sigma genre. What we're talking about is a passion of mine at capability metrics. I'm not sure your background, so we'll start a little bit about CP and CPK, the most common of the capability metrics. I started using them back in manufacturing when I left the service, 1980s, and they've always given me heartache. And again, that's some reason why I put this all together. So we're talking about the theory behind them. Bring up the concept of confidence intervals. Now, if you're a Lean Six Sigma or somewhat statistically adept, you'd find that everything we ever calculate has a confidence interval. So if you predict a number, a mean or a standard deviation or anything calculated, there is an uncertainty behind it because you're only using a sample of your data to calculate it. We're going to talk about confidence intervals. I've got 3 different simulations I can run. I'm not sure what we'll get to today, but I want to show you how you can use simulators at some level to test theory, which is really what this is about. Most of the background for the math I'm taking out of a book that the owner of my company, Smarter Solutions, wrote. It's called Integrated Enterprise Excellence, the Improvement Project Execution Guide. It's a handbook of doing Lean Six Sigma DMAIC projects, but it's got a good statistics textbook section in it. So let's talk about CP, CPK. These are called capability indexes, and if you're in the quality field, you also understand there's a PP and a PPK, where C is intended to mean a batch or a sample capability, where if it's a P instead of the letter C, we call it the performance or the population capability index. Math is the same. The only difference is where the standard deviation comes from. So I'll talk about CP, the capability index, and the CPK, which is still called this capability index, but the K means it's adjusted. The equations are on the screen. So the potential capability, or CP, is the width of your process requirement, or your specification, divided by 6 standard deviations of your process. The concept is if this ratio is 1, your distribution is about as wide as your specification. Right? It doesn't say anything about how it's centered, it just says what you could do. So when we're talking about the CPK, which really looks at only the capability on the side that you're closest to the specification. Now, if you're a nerd like me, you'd understand there's a K in there. What's K mean? And it comes from a correction to the original CP equations were shown. And it's on the screen. It's just the difference between the mean and the standard, the mean and the specification divided by really half of the process width. Not a big piece. Let's talk about CP and CPK and what do they really mean. What you may not realize, or what I didn't realize when I was taught, is that idea of the 6 standard deviations or 3 standard deviations on the CPK on one side. If you really are going to use a capability index to discuss your capability or your performance of your process or product, you really don't care about standard deviations and mean. What you care about is the fraction of the items, transactions, or products that would be considered non-conforming or outside of your requirements. Now, to make the CP and CPK translate from a common number to a capability of defectives, there's some assumptions that they don't talk about. One is the process should be normally distributed. The whole concept of plus or minus 3 standard deviations bounding most of your product only exists for the normal distribution. And we'll talk about that a little bit on. There's an idea of independence. All the data points must be correlated when you calculate your standard deviation. If they aren't, it can bias it to be either high or low based on your data. Independent means that they're really a random sample. And there's an issue of stability which was never talked about. If your process is not stable, it's not really worth reporting any capability because it's not stable. Now, why does this come up? I mean, if everything is done right, if you get a CPK of 1, which means the specification is 3 standard deviations away from the mean, in a normal distribution, that's 99.73% of the data should be bounded by those limits, which means you should have less than a 0.3% defect rate. Now, that's what the theory says. But if you're in practice, most companies that use this have a target of a CPK of 1.3, which means the specification is 4 standard deviations away from the mean. In that case, you should predict near 0 defectives, but those of us that use it still have higher levels of defective. So we use it thinking normality, but in practice it never exists. I have had cases in my manufacturing environment that we had a CPK greater than 1, which means the specification is more than 3 standard deviations away from the mean, and we would have 3 to 5% defective in a lot. Now, if everything is right, there should be no defectives with that level of capability. But I don't know, back in my early life, we never questioned why that was true. We just kept raising the target from 1.3 to 1.6, even to 2, hoping that if we asked for enough, we would finally get what we wanted, which was really a capability index of 1. So what was really wrong? Now, I know the math wasn't wrong. What's wrong is we didn't meet our assumptions. And that's what we're going to talk about, the assumptions. Well, again, I talked about earlier that everything you calculate has a confidence interval. Mean, standard deviations, coefficients, but why not CPK? Well, it does. They're hard to find. I found the first reference to it in a textbook, and I also found it on an online stat manual that the government puts out at NIST, which is really a wonderful online reference to statistics. But it was there. It gave me equations. As it pops up on your screen, there is the equation. CPK, confidence interval, is the estimated CPK from your sample, and then you can see a equation there. It's got a Z statistic, which is the probabilistic measures from a normal distribution. Then it's got an indicator there, which is really the standard deviation estimate for a CPK. Now, if you know it, it makes sense, I guess. N's in the denominator. When the sample size gets higher, your uncertainty would get smaller because you can estimate better. That makes sense. But also, as the CPK gets bigger, the interval will increase, which you can see because CPK is squared. It's also in the numerator of the right-hand term. So that makes some sense. Higher CPKs mean that you're farther away from your standard deviation. But it also means there's a lot more uncertainty because the long tails on the distribution are harder to estimate. So that all makes sense. Now, what I didn't realize when I put this together, and I actually realized it practicing yesterday, is this assumes there's symmetric limits, because you notice it's plus or minus the same constant from estimated. Now, we run the simulation, we'll find that that isn't true. So I'll show that in truth, this equation isn't right. It's a normal approximation, but it's close enough. This is what we're going to, when we run the simulation, this is the summary of a whole bunch of them. Oh, I'm sorry, this is the calculation from that equation. This assumes if we really have a population with a Cpk of 1.3, in other words, the standard deviation is the limit is 4 standard deviations away from the mean, it provides the confidence interval of what you might get from a sample. Now, the sample size is on the bottom. You see a sample size of 10. I don't know if you can see my mouse or not on here, but that's a sample size of 10. It really means at 10, it's somewhere you could actually get a number up to almost a Cpk of 2. But you can also get one down to about a 0.3.4. So given a Cpk 1.3 for the population, I can draw a sample of 10 that could indicate that I'm incapable or that I'm extremely capable. Now, as you walk through, you can see the more you get as it runs to 150, the uncertainty gets smaller. But I thought it was interesting, up to a sample size of, I think it's 47 when I went down to look at it, you can actually have a very capable process that should have no defects and still get a sample that tells you that may not be true. Confidence interval drops below 1. All right. Take that concept. I'm going to go back a slide. This assumes you have a Cpk of 1.3 in the population. It talks about what you could get in a sample. Let's turn that around. What if you drew a sample and had a Cpk of 1.3? How bad could it be? Meaning, what could be your true defective rate in your population, even though you took a sample that said you should have literally no defects? And this shows right here, the upper line is the upper confidence interval for how high the defective rate really could be in a batch, and you still measured and reported a Cpk of 1.3. You can see in small samples under 20, you can still have 1% defective in your lot and have the computer telling you it should be less than 1/100th of a percent. So it does say that the Cpk's uncertainty is really horrible. Now, I don't know how many of you actually use it. I'd be interested if you'd put in on your chat, I can't see it at the moment, but put in a chat how many of your companies actually use CPs and CPKs. It'd be interesting to me. I may ask later how many of you understood that this is a real risk, but I see a lot of clients that have a requirement of a Cpk 1.3 by their suppliers, but they still have defectives. This could be why. Small samples. Let's go make a quick look at this. I'm going to come away from this and run a simulation. I'm not sure based on your screen, your resolution, how well you can see this, so you may just have to play along a little bit. I think I can make it a little bit bigger. What I have here is I am going to make a simulator that's going to draw standard deviation. It's going to draw a random set of data. I'm going to do some that have 10 samples of 10 and then some that go to samples of 25. I'm going to calculate the standard deviation based on the long-term rule, which is the standard deviation of all the data, but also use the one that's recommended for CPKs by the AIAG, which is the Automotive Industry Action Group, which sets the standards for this primarily. We'll compare the two results, two methods of calculating standard deviation. What I really want to show you is what is the true variability of a CPK that's calculated from a known population. So let me run at risk. I'll show you how it's set up right now. I'm going to do, I want to change that. It's going to just run 1,000 samples, but I'm only going to run one set of it. So let's run my simulation. You saw there in the screen what the answers were, but I'm just going to make you live through another simulation. I did it ahead of time so you would see, so I can show my charts on the same scales. I talked to Jameson early. I probably is a way to go do this, but I'm not a specialist. I'm actually just a user. What I have here is, let's look at the CPK of samples of 10 using the overall standard deviation. I think I can make this bigger. This is given a, oh, I didn't tell you, this has got a, get back out of this, make it smaller. This was created with a data set and a random population that really has a Cpk of 1.3. So that is the true Cpk of the population I'm sampling from with my Monte Carlo system. Now what this shows me is what Cpks actually came out. You can see I had numbers down well below 1, and I had some calculations that went up over 3.5. Now what's the average? It came up a little above 1.3. It says 1.45 is the true average Cpk that was generated from a distribution which has a Cpk 1.3. Now why is that? Well, it comes about because it's a skewed distribution, and if you'd learned it, when you have a skewed distribution, your mean always biases high. The median of this is really, if I can check it, comes up at right about 1.3. I think I can drag this over till it says 50%. Close to the median, you see it's 1.37. So it shows the distribution is pretty good, but it isn't symmetric. So I have up here the 80% confidence intervals if I go back to this. Put a 5 in here. This really says the 80% confidence rate, or 90%, 5% above of my answers will be above 2.1. 5% of my Cpk samples were below 0.9. Notice it is not symmetric about 1.3 because it is non-normal. This tells us right there that that equation I showed earlier isn't right, that I'm biased to getting above average numbers. So in other words, the average Cpk reportedly better than the population. Another reason why Cpks sometimes lie to us. Go look at the other ones. If you look at that one, it went from 0.9 to 2.2. Let's look at the same sample of 25 using the overall. You notice this, it actually is a little better. It's 1 to 1.8, so the uncertainty is lower when I take larger samples. Well, that in the equation shows it to be pretty good. Notice what I'm really doing, though. I'm using a Monte Carlo simulator at risk to verify the theory that was given to me out of a textbook that's been sourced, and it is the best estimate for the confidence intervals. All right? So again, I'm showing theory wasn't right, but it was close. Now let's look at the difference with comparing the full calculation versus the standard method, which is the AIAG method, the R bar over D2 method. In this case, it's actually got more uncertainty. It says it goes from 0.85, the other one's around 0.9 for a sample of 10, to 2.4 from an vary about 2.1. So this says if you actually use the traditional method, which is to measure your CPK, you really are uncertain with sample sizes of 10, which a lot of us think are just fine. If you go use AQL sampling methods, which I'm not talking about here, they recommend sample sizes of 10 and 13 for batches up to 70 to 100. And if you've never gone to the statistics behind that, it is terrible. Don't use it. All right, go back to my presentation. What I've shown is there really is an awful lot of uncertainty in CPK for sample sizes even up to 25. All right. But that was just assuming you really have the right kind of data, normally distributed data, just like it's supposed to be. But what if you don't have normally distributed data, which does happen? I don't know. Let me see if I can look at the chat. Has anybody sent me a note yet?
I don't think so.
I just got one that says they somewhat enjoy it, so thank you.
Oh, good. They're good ones.
But if you say the presenter's doing a good job, it's always a good comment. So feel free to put them in, though. It does help me give my presentation. Let's look at a mixture. What happens if you have not just one population, but a mixture of two? This you'd find is if you're bringing in material that they mix two production runs together, or maybe it's a combination from two different people that were processing it, or maybe two different manufacturing lines, 2 different days it was produced on. But really, the world's never ideal and perfect. There's always issues. So let's talk about a mixture. So they send you material that isn't homogeneous. Well, how do we evaluate that? Well, first of all, we're going to use the simulation program because it is the purpose of this webinar. Well, let's talk about our assumptions. Let's say we have two normal distributions that our process is generating. What we'll do is we'll match them to say they were identical, and we'll slowly move the means of the two processes apart to see where the Cpk, or the capability index, starts to cause more uncertainty than we showed in the last discussion. We're going to use a really neat function in Minitab called the risk sim table. So that'll be sort of fun. But we're going to calculate the actual percent defectives that existed in the process, since I know it truthfully because I use a simulator, versus what the Cpk that would be reported would make me think should be the defectives. That's how we're going to look at this. First question is, how much shift of the process makes it look bimodal? So I used a different simulator program than at-risk, one that simulates pictures. But this would be a case in the top left is where you shifted the second process 1 standard deviation, then 2 and 3. What you notice is a shift of 3 standard deviations of the second process data. You start seeing this bimodality, or 2 modes, 2 peaks. When you only shift 2 standard deviations, it may look normally distributed. It's still got a single hump. Sort of looks a little bit like Mount St. Helens does right now, since it blew its top off, rather than a mountain range. So this is telling me the range that I want to simulate. I want them to have no shift, and I should probably go to up to around a 3 standard deviation shift to the mean to thoroughly analyze what mixed processes actually do. In my simulation, I tried 2 sample sizes. You probably won't look at both of them. I set a specification off the main process, a little bit off center, and I looked at standard deviation shifts from 0 to 4. And I'm going to do 4,000 of each one. See what it looks like. I'm going to go to it. Now, one of the things with at-risk is it'll run the simulator on everything you have open at the time. And I really don't want to run multiple simulations. So I got to open one and also close the other one. So I want to close this one. It's actually hidden behind my screen, so let me go this way. This is the one I want to close. All right. Here we go. So what I have right here is my simulator I'm going to use. I can make it a little bigger. I'm using the risk sim table. I have it in blue here. Those are the standard deviation shifts I'm going to run in this time. I ran it up to 4, but it takes too long, so we're going to run it up to a shift of 2 for you. It's insert here, so this is the shift. There's 2 different means for my 2 populations. Here is my specification, and I've colored the data points here. What it generates is this is a random normal number with the mean in the first population, standard deviation of 1. I've turned them blue when it's mixing in the second population. So if you look at the first one, the mean is in row 4, and the blue ones are in row 5. So I did it with 25 values, and I did a group of 50. So I've got 2 different populations. Everything in red here was accumulated as a risk output. So here is my actual predicted defect rate between samples of 50 and samples of 25. But here's the true defect rates given the 2 distributions, because I can actually directly calculate them since I know truth. The interesting thing I threw in this one is, well, what would a normality test, would I have detected the bimodality or the non-normality of the samples? So if each sample I'm running, I'm doing a normality test using the Anderson-Darling method. Now this is, I took this off the internet, and just to show that we're all honest, here is the screen does show that I can use this freely as long as I say where I got it, and it's shown here. But what it does, it calculates the p-value. Now I made a risk output of the p-value that we're going to make a plot of it. So that's an interesting seminar in itself, was how do p-values from a hypothesis test actually distribute. And I was fascinated on that. I actually did a webinar internally in my company last week about that topic. It's available on our website, smartersolutions.com. Let's go look at this. Let's go run it. Again, please ask questions. Now, if you note here, it's going to run, I'm going to run 1,000 each one instead of 4,000. I'm going to run all 5 of my conditions right now. So, by the way, if you didn't know it, this software does help with multiple processors. I don't see the little, there usually a screen pops up. It's probably got something to do with the webinar that talks about how the processors are running. But it will share the processing capability of each of the 4 cores on my processor. I just think it's interesting. Yeah, it looks like it's finished up. If I can look at my table of answers, we'll walk through them real quick. The first one is the true predicted defect rate. Well, it turns out that since I had a standard distribution, it is the same number every time, but it should have been about 0.5% defective. Oh, where's the mean? There it is. This is the 99.73 defective from the base properties. Well, that's what you'd expect. Then I can look at the Cpk estimated. What you'll notice is these are the shifts you'll see. When you have 0, well, you run through these, what you'll see is there's a big difference in Cpk calculations. They start really changing the percent effective as you run through your table. I really want to go clear to the bottom of my accumulations here. This is the predicted out of specifications using my normal assumptions. I made my shift. I should get up to 5% effective when I get to the higher end of my simulation. I'm going to shrink this back down. There we go. So when I look through this, I can look at different things. My predicted out of spec. This is using the normal assumptions, and I can walk through. This is no shift up to the higher shift of 2 standard deviations. Oh, it's behind the screen. There you go. But I can see that I was predicting about 5% really out of spec if I believed I had a normally distributed data and used my Cpk calculation. Now I can look at my Cpk at the same time. The calculated Cpk in this case dropped down to about an average of 0.7, 0.65 is I got the bimodality. So as my data shifted, my Cpk did the right thing. It shifted to lower values. I can see if my means right here. I'll scroll up a little bit. There's my Cpks. It ran from what it should have been, an average of 0.04, and it ran down, and it got more and a higher and higher average defect rate. Here it is. Went from a Cpk of 1 and got lower and lower as the mean shifted. So it makes sense. I started with a Cpk about 1. As the second population shifts, the Cpk drives down, but the real issue comes up is what happens to the defect rate? Okay? And the defect rate runs down. All right, and one thing I didn't show you was, I got to get my table back up. Oh, cancel. I did this once before. When I ask for the wrong thing, sometimes it doesn't like me. That's not all my results. Well, I hit it. Now I'm not sure how to get it back. I think I can get it this way. Nope. There you go. I hit it behind the scenes, and it's not showing me. Right. Let me go back to my slides. So here's what the results were of it. This is the chart of what the defect rate was predicted as I ran the shift up. Well, you notice that the defect rate should be close to 0, but it drops off rapidly as the process becomes bimodal. As I showed you, at the point of a shift of 2 sigma, it was flat on the top, but as I went to 4, the standard deviation started, or the shift showed it to be 2 mode. So again, does that make sense? Yes, and you can look, if this is the point with the 2 sigma shift, it doesn't look that non-normal. So again, it's pretty close to working. What you find is you get bigger shifts, the Cpk starts saying that you're non-normal, and you end up getting a lot more defectives than you'd expect. We're about halfway through right now. It's 11:30. I hope I'm keeping your interest. Again, please ask questions if you have them. Next one's, what if you don't have normally distributed data? The assumption I haven't talked about. Everything up till now has been relatively normally distributed. Now, what's non-normal data? Well, generally, it's just not symmetric or bell-shaped. I'm going to use a log normal distribution for the next simulation. Now, where do you see that type of data? Well, really, if you're ever collecting times, the duration it takes to do something, time to deliver, time to manufacture, time to process an invoice, time that you take waiting in a call center to be answered, the time it takes to handle a call in a call center. But also, yield data is non-normally distributed, counts and such as that. Now, in the Lean Six Sigma world, these happen all the time. Now, depending on where you get trained, you may or may not have seen the handling of Lean Six Sigma data that's non-normal. My original training, I think I saw one of the participants came from Florida Power and Light. That was where the trainers in the company I got originally trained on came from. And they didn't teach non-normally distributed data. They just, it was normally distributed or to use what they call non-parametric tools. When you really learn what this non-normality means, you can get an awful lot out of it. So we're going to walk a little bit there. Here's a diagram out of Minitab that shows what log normal data looks like. Now, log normal data's got two parameters, like mean and sigma of a normal distribution. They have location and scale. Location's sort of like the mean, scale is sort of like a standard deviation. Each plot here has got a scale change with the same location parameter of 2.2. But if you look at the charts, they start out with a small hump and a long skew to high numbers. But as the scale number gets larger, it gets to a sharper and sharper, I guess it gets smaller, it gets to a sharper and sharper peak. Now, these are the parameters I'm going to use with, at risk, using, again, the risk sim table. It allows me to do what ifs. This is what the non-normality looks like. If I take these distributions and plot their percent defective as I change the scale value, you see the percent defective gets low but starts skyrocketing as the scale shifts. What you're really seeing is the effect of the non-normality. If I go back, these are really highly defective, these really skewed distributions, but when you get the very sharp one, in other words, a low scale, you don't get that many more defectives than you expect with a normal distribution. But since this isn't about that, it's about CPKs, what we're going to find is this data that I'm going to use, I've forced it to have a CPK of 1 by the way I calculated it, which means I took the mean and the standard deviation of each random sample and set the specification so that it would be a CPK of 1. And then I calculated the true defect rate that exists in the population. Well, if it is normally distributed and it is a CPK of 1, I should have about 0.27% defective, which means the 3 standard deviations include 99.73% of all the data. So as I deviate away from 0.2 or 0.3% defective, you can tell that that's the non-normality of the log normal distribution. Now, I'll show you the simulation. Again, I need to close one and open one. I'm going to run it. Log normal scale. Very similar to the last simulation. What I have here is 25 and 50 values, each log normally, risk log normal. There's the location and the scale values. My specification is calculated directly from the distribution I'm using. Here's my risk sim table. I go from 0.05 up to 0.8 for my shape parameter, or my scale parameter. Move the results over. I calculate the percent out of spec for a 25 value sample and a 50 value sample based on the CPK or the normal distribution assumption, what it tells me I should get. And then I've got a direct calculation of the log normal distribution by what it actually predicts. And I calculate the normality of each data set. I think I'm using the 25 sample one. What we'll find going through here is the normality of my sample deviates from, I guess as a deviation, the distribution deviates from normality, you'll find that the error in predicted defectives changes also. Now I'm going to run the simulation here. In this case, my risk outputs are the normality, or the Cpk. The normality test, I'm also calculating the predicted defectives and the actuals. So if I run this simulation, 1, 2, 3, 4, 5, 6, 7, I got 8 choices. I'm not going to run them all. I'm only going to run 5. So it's giving me an error because I have some that I'm not actually running, but I don't want to run them all today. So I can look at each one. This is what I really care about here. That one's a standard. Should run over here. It's running through the simulation. I don't know why during my webinar, but there's usually a box that pops up that tells me how my simulation's running, and it must just be a nature of the webinar. It's not popping up.
It's a conflict of WebEx and Windows 7. And I have a little plug-in I can send you.
Probably won't matter on the webinar.
Oh, looks good though.
Yeah, it works when I use a different system, but it doesn't matter. I can sort of see when it's done.
Yeah.
Yeah, because I have I can move my charts again. If I look over my results, I scan down through them. Here's my charts of the p-value for my Anderson-Darling test. What's interesting is I go through this. This is the low-end number, which is relatively normally distributed. This chart is relatively flat. What I have here is the 5% of the out. You can see that I get a whole range of p-values that are around 0. It's uniformly distributed, which is what you'd see for normal distribution. But as I drift and increase the scale value with my risk sim table, the p-values start driving to be primarily small. Again, in this case, we'd reject normality at a 0.05 value for the p-value, which if I put in 0.05, oh, no, I want 0.95, I guess. What you'll see is here's 0.05 is right here. I put 0.5. Too many zeros. Come on back. I guess I can drag it. I want this to be 0.05. We see I have a higher fraction. I have a lot less than 5% left over here as I run down here. When I get to the big shift, which was the related scale value, when I move this over to 0.05, on the p-value axis, I still have a huge peak down here. So I'm getting really over half the values showed to be non-normal, which tells me a lot about what my defects are going to be. So here's the actual predicted defectives on this process based on the Cpk is less than 1%, which is what we'd expect. But when you actually did it, the true defect rates come out quite a bit different. That's what I'm trying to show you. I guess I should have talked to Jameson about the plugin so it shows you some more stuff when I'm doing a webinar.
That's my fault. I'm sorry.
I didn't know it. But it doesn't take away from your learning lesson.
No.
Just because you can't see one screen doesn't matter.
No.
What you find here, though, is that between 0 and 50, the defect rates really climb up from what you actually see to what the yield is. So you under-predict the yield using Cpk when you have non-normally distributed data. So here's the summary after I took out of what at-risk gave me and plugged it into Excel to make a different type of chart. What we're seeing is the percent that you get a value of a low p-value, which means non-normality. When I get to the end, oops, I went too far, 80% of my samples say I'm non-normal, but they're also now I'm underestimating the true yield by almost 3%. What we're seeing is the track as your data derives away from normality, you end up underestimating your true yield. So your Cpk is going to make you think you are better than you actually are. If you're a user of CPs and Cpks, you already know that that happens. So we've given you really 2 reasons the Cpk will underestimate your defect rate. So here's my conclusions on the capability index one. We often ignore the assumptions, the normality of the original data, and that it's a homogeneous, independent data set. And I looked at two mixtures. So if it isn't a pure process, you've mixed processes together, as in people or shifts or batches or whatever, the CPK will underestimate your true yields. So you may see a good CPK and have defectives in it. The more bimodal or shifted the two processes are, the more it will underestimate your true defect rate. And the last one was on non-normality. Is the data ceases to become normally distributed and is shifted, such as its time or duration, such as that, you will find you also underestimate the defect rate using CPK. So really what it's saying is CPK is not a great capability metric. It's not really giving us what we'd like, which is a measure of defect rates, which is why we talk about it in our Lean Six Sigma classes here at Smarter Solutions, that you surely avoid using it unless all the assumptions are true, and when you get down to it, most assumptions are never true. You're better off directly calculating defect percentages or predicting them. You'll find that's a lot better measure of capability and performance for your business. So what did I use at-risk for? Well, the first one was I used at-risk to test the theory that I got out of the textbook. Now, if you get to some point in your life, and I'm an older guy, you find that books lie. Well, that's not true. What books don't tell you the whole truth. They give you what you need at the time. I work with my kids in high school right now doing math, and I clearly see they only teach you part of the theory as you're at a certain point in your learning. We don't know that there's more beyond it because that's not what we've been taught. But at-risk lets you go test the theory they give you and realize if it's good or bad. The second one is you can use those risk sim tables to vary the assumptions in a test and see how it changes the answer. It's a wonderful one. My webinar last week was about running t-tests and hypothesis testing. That if you can change the assumptions of the hypothesis test and watch how the decision changes. It's wonderful. Use it to show what alpha and beta risk really mean by running a bunch of random numbers. And I guess my love for this topic came about from a mentor I had in my last employer. He said, don't worry about theory, it's too hard to calculate. Just use the simulator and generate an empirical probability relationship, and that will tell you better than you can ever get with math, pencils, and papers. We used at-risk there, and it was wonderful. You can get things done in an hour that might take you 2 weeks with a pencil and paper. That's why I used it. Well, I hope you got some out of the webinar. It's like 45 minutes. There's time for people to ask questions, which nobody has yet.
Thank you so much. Yes, let's see if we have any questions.
I would ask think about it. Enter if your company uses CP and CPK. I'd like to also just comments too if you think this taught you something. Was it worth your time is a great question too, since we didn't use polling. I'm not getting a lot of response.
We'll wait a minute.
Maybe one's going to come up.
Here's the question. Are yields referring to percent of defects or percent lack of defects?
Well, honestly, the theory goes both ways because it's one minus the other. I used in this case to predict the percent non-conforming. It may be a defect, but it could also just not meet a requirement. So yeah, I was predicting that the percent that was not meeting the requirements was actually larger than you would have expected using the Cpk measurement. That's what the point of this was, and the way I showed it was using a simulator to assume a distribution and then calculate Cpk, and since I knew the truth, the actual percent defective could be calculated.
Mm-hmm.
But I could have easily have used the percent conforming in the same way. All right, thank you for the question.
Yeah.
All right. Well, if you enjoyed this, I think you have the choice. My contact information may be provided to you. It's rick.h@smartersolutions.com. I don't think I put it on here.
Is that okay if I send all that out to our...
If you would like copies of my simulators, just ask. A copy of the presentation is also available in a PDF form if you're interested. I know as a user of at-risk, sometimes you just want to see how other people simulate stuff to help. It's a quick way to teach. It's available to you.
Thank you for that. Oh, you
I
mentioned...
think that's all I have, Jameson. If there is another question, I guess you can wrap it up.
You mentioned time data. Can you give examples?
Let's say you're in a business, and I can take it to one. You have a on-time delivery goal with your client. You tell them that you will have 95% on-time delivery. Well, so really you're shipping a bunch of stuff, and you want to know what's the capability of meeting that goal of, let's say, 2 days. You're shipping 2 days. So you can collect data, and a lot of shipments come up and say, well, I have a Cpk of 1.3 against my 2-day shipment goal, which really means nothing should be late. But I'm finding that I'm actually getting late product delivered. Well, that's probably because when you measure the time it takes to deliver, that's a log normal distribution generally. Now, log normal because you can't really, it's the time it takes to ship something, which can never be negative. So the only thing you can have is time greater than 0, therefore it skews the data. I like to think of it in time data. When something goes wrong, it never makes it get there faster. All it can do is delay things. So you generally get a typical result and then a tail of errors that are a longer period. Another one might be the time it takes to answer calls in a call center. All right? Your job is to answer your call. I would say Microsoft for a PC problem, but I realize that's probably not a good choice. Let's say you call your cell phone company because you want to understand your voicemail isn't working, you want to get it fixed. Well, there's a time they call it the handle time in call centers. They would plot that, and if you're trying to, you have committed to all the companies that you're going to handle all calls within 5 minutes. Well, you can measure the length of all the calls. The distribution would be skewed like a log normal. And if you took Cpk of that against my 5-minute goal, it would make you look a lot better than you actually are. Because in reality, with the tail going out the longer times, there are some calls that went longer. You have a higher percentage that would have exceeded your limit or non-conforming if you directly calculated it than if you used the Cpk.
Oh, good explanation.
All right.
Yeah, thank you. Well, maybe we have time for one more, say?
All right. Well,
yeah, if one comes.
Noon, so, or at least noon here Central Time in the U.S. But ask another question if we have one. And I guess I should also plug my company. I appreciate At-Risk giving me a chance to do this. But again, this derives from the work I do. I teach Lean Six Sigma, some of the belt training, and do consulting. But this is a common topic we deal with our clients with, of not understanding their quality and wonder why it says it's good, but it isn't. And that's what this whole topic drives from. And we use discussions similar to this to talk to our clients of why maybe the way they're reporting their quality is leading them down the wrong path. Makes them feel better than they should be. Do we have any more questions, Jameson?
I don't think so, Rick.
All right, thank you, everybody. I appreciate your time. Middle of a big day.
Yeah.
So have a great day, and
thank you for your time. This is great. Thank you.
Good luck.
You too. Thanks.
I think you can take control of it again, Jameson, and we're done.
Yep.